topic of discussion is hydraulic stress, volume strain. Okay, these are the topic of discussion. Now in this figure which is shown here, okay, a solid body is placed in the fluid under high pressure, is compressed uniformly on all sides. So this is a solid body which is placed inside the fluid and it is compressed from all over. Okay, the force applied by the fluid acts in perpendicular direction at each and every point on the surface, and the body is said to be under hydraulic compression. So each and every point is experiencing the force which is locally perpendicular, and because of this, what happens? This body is having hydraulic compression. Okay, as a result, this leads to the decrease in its volume without any change in the geometric shape. Generally we say volume remains constant, but here volume is reduced, or we can say it is changed. The body develops internal restoring force that are equal and opposite to the surface, or we can say it will be equal and opposite to the forces applied by the fluid. Now try to understand. As fluid is applying the force in this direction, the internal force will be in the opposite direction, and this force will try to bring the body back to its normal original position. The internal restoring force per unit area in this case is known as hydraulic stress. Again, force per unit area, that is internal restoring force per unit area, is known as hydraulic stress, and its magnitude is equal to hydraulic pressure. Okay, the strain produced by the hydraulic pressure is called the volume strain, and it is defined as change in volume to the original volume, that is delta V upon V. So delta V upon V is volume strain, generally denoted by epsilon V, and this will also not have any unit. Okay, now the topic of discussion is Hooke's law. Now Hooke's law is stated like this: for small deformation, this is very important, small deformations are there, the stress and strain are proportional to each other, or we can say stress is directly proportional to the strain, or we can say stress is equal to some constant into strain. Here K is the constant of proportionality, which is known as modulus of elasticity. Its name is modulus of elasticity. Hooke's law is an empirical law, means it is derived from the different experiments by taking different material. Okay, and it is valid for all the material almost. Okay, however, there are some materials which do not show this linear relationship, that is stress is not directly proportional to strain for some material. Now if you want to find the SI unit of this constant K, then that will be Newton per meter square, or it is Pascal, and its dimensional formula will be m1 L minus 1 T minus 2. Now there is a graph of stress versus strain curve for a metal. Okay, stress strain curve for the metal is shown in this figure. So this figure shows the stress versus strain graph. Here this is the graph which I am just showing it to you. Okay, so this curve is a stress versus strain curve. Okay, now from the graph we can see that in the origin, or rather in the region between O to A, the curve is linear. You can see this curve is linear between O to A. In this region, Hooke's law is obeyed, means stress is found to be directly proportional to strain. The body regains its original dimensions when the applied force is removed. whenever you remove the applied force between this section, that is OA, then the body will come back to its original position. In this region, the solid behaves as elastic body, means it will regain its position or regain its shape, size, everything. Okay. Now in the region from A to B, stress and strain are not proportional. You can see between A and B, this region there is a curve. This region is having the curve. Okay. In this curvature part, we can say that this stress and strain are not directly proportional. The body still returns to its original dimensions when the load is removed. In this particular region, that is between A and B also, if load is removed or applied force is removed, still the body will come back to its original position. The point B is known as the yield point. Its name is yield point, means this point B is a yield point. Okay, where you can yield the original shape and size of the object, or original shape and size of the object can be obtained, regained, we can say. Okay, this point also known as elastic limit, and the corresponding stress is known as yield strength, that is sigma y of the material. So whatever is the corresponding stress is known as the yield strength, or we can say from that point still the material can come back to its original point or position. If the load is increased further from point B, the stress developed exceeds the yield strength and strain increases rapidly, means change in length will be seen. If you still increase the load after this point B, applied force is increased after point B, then the change in length will be seen in a more amount, we can say. Okay, and more stress is developed. If the load is increased further from point B, the stress developed exceeds the yield strength and strain increases rapidly. The portion of the curve between B and D shows this. When the load is removed, say at some point C between B and D, the body will not regain its original dimension. Try to see it. Okay, from B to D, if you see from point B to D, now if the load is removed between this point, at any point, say at point C you are removing, then the body will be permanent set, or the body will be deformed. It will not take its original position, it will not regain its original shape and size, and some deformity will remain. Okay, so up to B the load is removed, then again the body will come back to its original point, or original shape and size is removed. But between B and D, if you remove at any point, if you remove the load between B and D at any point, then the body will be permanent set, or we can say there will be a deformity. Okay, body will be deformed. Okay, the portion of the curve between B and D shows this. When the load is removed, say at some point C between B and D, the body does not regain its original dimension. In this state, even when the stress is zero, the strain is not zero. Okay, because deformity will be there, change in length will remain. There will be a deformity. If there is increase in the length, then that increase in the length remains as it is. The body will not come back to its original position. The material is said to have permanent set. The deformation is said to be plastic deformation, means the object will not come back to its original shape and size. The point D on the curve is the ultimate tensile strength, that is sigma u of the material. After this, beyond this point D, additional strain is produced even by a reduced applied force, and there will be a fracture or the body will break. So up to D it can resist, or the body will remain. There will be a deformity, but if you increase the load after this point, then the body may break at any point between this D and E, and this E, wherever the body breaks down, is known as the fracture point. Okay. If the ultimate strength and the fracture point D, okay, and E are close, the material is said to be brittle. If this ultimate strength and fracture point D and E, okay, so D and E are close, then the body is said to be a brittle body. D and E are close, then it is a brittle body, we can say. If they are away from each other, then it is ductile. Okay, if they are far apart, then the material is said to be ductile, means you can increase its length. Okay, generally metals are ductile, while some other body, okay, they are brittle, like say the what you call it, the coal, charcoal. Okay, they are brittle bodies. Okay. What is an elastomer? Plot stress versus strain curve for it and explain. Materials which can be stretched to cause large value of strain are called the elastomers. Large increase in the length is there, large deformations can be produced, and they again come back to its original position and shape. Then they are called the elastomers. For example, rubber and elastic tissues of aorta are the elastomers. Rubber can be pulled to several times of its length and still again it regain its original shape and size that you know. The graph of this stress versus strain for the elastic tissue of aorta, okay, large tube vessels which are carrying the blood, they are shown here. There is a non-linear relationship between stress and strain. Note here that elastic region is very large, means deformation can be several times and again it can be brought into the same original shape and size. Hooke's law over most of the region is not obeyed. Okay, secondly, there is no well defined plastic region. Okay, so these are the characteristics of this stress versus strain graph for the elastomers. Now, what is elastic moduli? The ratio of stress and strain is called the modulus of elasticity. Okay, ratio of this stress, as such you know, stress is equal to K times the strain. Okay, so this stress upon strain is a constant quantity which is called the modulus of elasticity. It is dependent on the characteristics of the material but does not depend on the dimensions of the material. It depends on the type of material. It does not depend on the size and shape of the material. There are three types of modulus of elasticity: young modulus, then there is bulk modulus, or we can say compressibility, and there is a shear modulus which is denoted by G. Okay. Now, what is Young's modulus? Experimental observations show that for a given material, the magnitude of strain produced is same whether the stress is tensile stress or a compressive stress. Tensile means there will be an increase in the length, and compressive means there will be a decrease in the length. So experimental studies shows that for a given material, the magnitude of the strain produced is same whether there is a tensile stress or there is a compressive stress. Now the ratio of tensile stress to the longitudinal strain, because if there is a change in length, rather increase in the length is there, then it is a tensile stress. So tensile stress upon longitudinal strain, this ratio is defined as Young's modulus denoted by Y. So Y is equal to sigma upon epsilon. Sigma is force upon area. Okay, and you know that longitudinal strain is change in length upon original length. Okay, so it is delta L upon L. So F upon A upon delta L upon L. So if you simplify, then you will get F into L upon A into delta L. Okay, here strain, as you know, delta L upon L, it is the ratio of two lengths. Okay, change in length upon length. So it is having no dimensions or no unit. So we can say the Young's modulus will have the unit of stress, and that is Newton per meter square or Pascal. Dimensional formula m1 L minus 1 T minus 2. Okay, these are the Young moduli of different material. Okay, for metals, Young's moduli are large. Therefore, these materials require a large force produce small change in length. So if you want to change the length of these materials, then you require a large amount of force because their Young's moduli are very large. Steel is more elastic than copper, brass and aluminium. Okay, steel is found to be more elastic. It is for this reason that steel is preferred in heavy duty machines and in structural designs. Okay, wood, bone, concrete and glass have rather small Young's moduli. Okay. Now this is the experiment to determine the Young's moduli or rather modulus. Okay. There is a reference wire and there is another experimental wire. They are both kept parallel and they are hung by the rigid support A and B. Okay. Now this is experimental wire where some hanger is kept where you can keep the different mass or rather some mass can be loaded at the end of experimental wire. And this wire is kept parallel and 1 meter scale is kept where a pointer of this experimental wire can be set. Okay, and some mass is kept at the end of reference wire so that it can be kept taut. Okay, it can be kept straight rather. Okay, it can be kept tight, we can say. Okay, so here some mass is already kept. We don't want to change this mass. Okay, here in this experimental wire, try to understand. Now what do we do? Here some load is kept, some mass m is kept, so mg force is in downward direction. So this is the applied force from outside. Okay, before that we are measuring the radius of this experimental wire by using micrometer screw. Okay, micrometer screw is used to measure the radius. First of all, it will measure the diameter, make it half, you will get the radius. So radius is measured, then you are applying the mass m here in this pen. So mg force will be acting in the downward direction. So force which you have applied from outside, F is equal to mg. Okay, or capital M if you place, then the force will be F is equal to mg. Radius of the wire is already known to you. From this value of radius, you can find the cross-sectional area of the wire as it is circular cross-section. Wire is having circular cross-section, so its area will be pi r square. Okay, so stress sigma, okay, stress can be found. Stress is sigma, that is applied force. Force is equal to mg. Okay, force upon area is pi r square. So you can get the value of stress. Okay, so you are having the value of sigma. Now we want to find out Young's modulus. Okay, now see, stress upon strain is Young's modulus for change in length. Okay, whenever there is change in length, whenever there is elongation, we measure the Young's modulus. Stress can be found, as I have explained, it is mg upon pi r square. This way you can find the value of sigma. Now how to find strain? Before starting the experiment, before putting this load in this, okay, you just see where the pointer is on this vernier scale or this scale, we can say. Now put the load, that is m mass is kept here in this pen. Okay, wait for some time, say 10 minutes or so. You will find that this pointer will slightly come down. There will be a change in length or there will be an increase in the length. So initial reading you are having. Now after some time there will be a final reading of this pointer and you will find the change in length. Okay, so delta L is known to you. Initial length of this wire is given, or before starting the experiment note down the initial length of this wire. So initial length is also with you. Okay, so delta L, change in length upon original length, will give you the epsilon. Epsilon means the strain, that is longitudinal strain, will be obtained by you. Okay, so now you are having sigma, that is mg upon pi r square. You have this value of epsilon. Okay, stress upon strain, sigma upon epsilon, will give you the Young's modulus. Okay, so here it is shown sigma upon epsilon, that is f upon a upon delta L upon L, that is FL upon a delta L, will give you Young's modulus. Okay, and instead of f, we know that if m mass is kept, if there is m mass, then f is equal to mg. Okay, so instead of this f, it is written to be mg. L is the original length of the wire, pi r square is the cross sectional area A, delta L is the change in length, and if you simplify from different observations experimentally obtained, then y, that is Young's modulus, can be determined. Okay, thank you very much. Watch this 2-3 times and try to understand the theory part. Okay, thank you.